Here are the topics of today's lecture, which is the first lecture of deflection of a beam. Because this is the first lecture, I'm gonna give you some definitions and notations that we're gonna use in this chapter on deflection of the beam. After we discuss about notations and definition, we'll define and we'll learn about a so-called Euler-Bernoulli beam theory. And then after discuss about Euler-Bernoulli beam theory, we'll discuss about boundary conditions. So if you have taken any differential equation course, there is differential equation, and to solve the differential equation, you need boundary condition. And by combining the equation and boundary condition or initial condition, you can get the definite answer for that differential equation. So here we're gonna do same thing. We're gonna learn about a differential equation called Euler-Bernoulli beam theory, and we learn about boundary condition based on ME231 knowledge. And by combining these two as a first topic, we'll learn step-by-step procedures to get beam deflection curve. Okay, so hopefully you have this in mind. So in the first lecture on deflection of the beam, I will cover first topics, and in the next lecture I will cover boundary condition. In the final lecture of today, I'll cover the first topic. Okay, so let's begin from the notation and definitions. Okay, so in our textbook and in most other textbook, you will consider the left answer as origin of x, and we'll take x coordinate in horizontal way, and the beam deflection, which is the vertical deflection from the original position, will be defined as y as function of x, because depending on location, we're gonna have different vertical deflection, and this yx curve is called elastic curve. Okay, and when we consider elastic curve, we can adapt some knowledge from freshman calculus class. In freshman calculus class, we learn about radius of curvature definition regarding any differentiable curve, and from the calculus, the radius of curvature can be written as, if somebody gives you the curve, then out of this curve you can define and you can compute the radius of the curvature of this one-dimensional curve. And then what you're gonna see here is, out of this definition, we have 1 plus something square and divided by something second order differentiation. Here both second order differentiation and first order differentiation will be very small, because in ME231 we'll consider only very small deflections. Okay, so if the deflection is very small, and if the first order derivative is small, second order derivative is small, only the something square, small thing squared term will be much smaller than small thing. Because if you recall, how to take the squares, if you consider 0.1 and if you also consider 0.1 squared, and it becomes simply 0.1, it is 0.01. So when you consider very small number, which is much smaller than 1, and if you consider second power or third power, it will be much smaller than first power. So in typical linear approximation, which you have already done back in Taylor expansion course, after if the x is very small, the expansion range is very small, you can get rid of like a second order, third order, and fourth order expansion, and only with the first order diffraction approximation you can get reasonable approximation in small x range. And this is what you're gonna do exactly. So we'll ignore this second order term. After ignoring the second order term, you can approximate the radius of curvature in really simple form, like simply 1 over second order derivative of y with respect to 2. Okay, so that's the definition of radius curvature that we're gonna use in our lecture ME231, because we'll only consider small deflections. And then dy dx, this will represent the slope of the elastic curve. And if you take any x location, this is the location, and consider some angle theta x, what you can realize is tangent theta will be same as dy dx. However, as I told you, we're going to consider very small dy dx, and in that range, tangent theta can be approximated at theta. Okay, so in M231, where we're gonna consider very small deflection, theta x will be regarded as approximately dy dx, and it will represent the slope of the elastic curve. Elastic curve represent indicates yx. Okay, so it is elastic curve. This is radius curvature, but due to small deformation, radius curvature will be defined as this in M231, and the slope of the elastic curve will be defined as this in M231. So please remember these notations and definitions, to make our discussion easier. Okay, so let's move on to the so-called Euler-Bernoulli beam theory. So actually, even though I just telling you that some fancy name like Euler-Bernoulli beam theory, actually it's simply rewriting what we have learned back in chapter 4 regarding the pure bending problem and the derivation of a flexure formula and etc. So back in chapter 4 we derived this equation: 1 over rho equals to be m over ei. However, starting from here, we can connect this with elastic curve, because elastic curve indicates the local radius curvature is simply written as 1 over second order derivative of y with respect to x. So 1 over rho can be written as the square y dx square, which is this. Okay, then you can connect this second order derivative with the moment diagram. Okay, so back in chapter 5 we learned how to obtain moment and how to obtain the shear force as a function of location, and out of the free body diagram and the analysis, we can obtain the m as a function of location x. Then, having obtained m as a function of x, you can connect this to second order derivative, and from this second order derivative, you might be able to obtain yx if you have the appropriate boundary condition. Okay, and in addition to that, we can keep doing this for other thing, because we learn about the relationship in chapter 5. Okay, we learn about the relationship between vx and mx, and they are connected through this derivative relationship. So in the position of mx, if you plug in this equation, this is what you're gonna get about the relationship between vx and third order derivative of y. Okay, now after obtaining this equation, and you can also realize the distributed loading from the top, and the local shear force can be related through wx equals to be minus dv dx. Okay, and in the place of vx, if you plug in this entire equation, then you're gonna get like a fourth order derivative and the distributed loading external loading relationship. And these series of the differential equation is called Euler-Bernoulli equation. One thing you gotta be careful is that when writing down these equations, you gotta make sure that you define your mx, you define vx, you define your vertical distributed loading according to our sign convention. The positive sign for m indicates this smiling moment sign, and the positive sign for shear force v has different meaning for left-handing and right-handing surface, so you gotta be careful about this. And also regarding the distributed loading, we take the downward distributed loading as the positive sign. Okay, so you gotta be consistent of using these series of sign convention for defining m, v, w, so that you can use these equations, differential equations, usefully. Okay, so they are all linear differential equation, because you don't have any term something like this, something like this, something like this. Okay, you only have just one term, second order derivative, third order derivative, and fourth order derivative, and you don't have something scared. So we call this as linear differential equation. And the solution of a linear differential equation, you should have learned that knowledge from some any engineering math course handling the differential equations. Okay, so let me try to give you the relationship in small and summarized diagram. So in short, the external load W is connected with internal shear force Vx, and the relationship is given as this, which we have learned back in chapter 5. And internal shear force is related to internal bending moment, and the relationship is also the derivative relationship m prime equals to Vx. And then this internal bending moment can be connected to the geometry through this relationship, the relationship between radius curvature and the internal moment. And then this curvature can be connected to deflection or elastic curve through our definition from freshman calculus and the linear approximation that we're gonna adapt in EulerBernouliBeamTheory. Okay, so after combining all those reactions, we can connect the external loading, external distributed loading, to first order derivative of this elastic curve. Then we call this as Euler-Bernoulli beam theory. Okay, yeah. So, however, even though you have taken some lessons until now, you're still gonna feel a little bit unsatisfactory, because we learned that M would cause shear stress and normal stress, and out of normal stress, you can expect normal strain. However, when we learn about shear force, shear force somehow induces shear stress, which is defined as and can be obtained as VQ over IT. And out of this shear stress, you can have shear strain. Okay. However, when you see all those relationships, we have considered the first line, but we haven't considered the second line. Okay. So yeah, I made that discussion in the beginning of page 4. What is missing? Yeah, we didn't consider full contribution of shear force and shear stress and resulting shear strain. We didn't consider this at all. We only consider this through 1 over rho m over EI relationship. Okay, so actually in practical way, it's okay to do this, because our ancestors already proved this. If we consider high enough aspect ratio, if the ratio between L and D is larger than 10, the effect of this guy, shear force, shear stress, and shear strain, is negligible in determining the elastic curve and deflection. However, if you have relatively small aspect ratio less than 10, this contribution should be need to be considered to take correct elastic curve, and it is called Timoshenko beam theory. Okay, so even though we're not gonna consider the full derivation of Timoshenko beam theory, actually sorry about this. We'll revisit this problem briefly in chapter 11, where we consider energy method, because based on energy method, we can account for this effect for some special type of beam bending problems. Okay, so our scope will be stay here, and in small aspect ratio beam, it will be beyond EulerBernouliBeamTheory. However, even though it's beyond EulerBernouliBeamTheory, we will briefly touch this problem in chapter 11. Okay, so from now on, forget about this. We'll just visit this in chapter 11 in beam deflection lecture, which we're gonna take from today. You only need to remember the first line. Okay, we'll just consider large enough aspect ratio and Euler-Bernoulli beam theory, and we'll learn how to solve this differential equation to obtain elastic curve using boundary condition. Regarding boundary condition, we'll discuss about it in next video.